In example 13.5, we're going to find the minimal muzzle speed needed to shoot a shell straight up to a height above the Earth that's equal to the Earth's radius, as shown in this leftmost diagram. So the shell starts on the surface of the Earth, which is a distance RE from the center, then it ends up in this final position, which is a distance of 2RE from the center. In the second part of the problem, we're going to calculate the muzzle velocity necessary for the shell to completely escape the Earth. So let's start with part A. We're going to use conservation of energy, where our initial position is on the surface, and as I said before, the final position is at point 2, and at this position, the velocity of the shell is equal to 0. So this is basically a generalized maximum height problem. We're going to need to use the general form of the potential energy due to gravity. Plugging into the equation for the initial and final positions is shown. Here's our potential energies, and here's our initial kinetic energy. And as I said, the object is momentarily at rest at this maximum height, so we put in 0 for K2, and we can immediately solve for the velocity that we're looking for. Putting in the numbers, we'll get 7,900 meters per second, which is about 18,000 miles per hour. In part B, our final position is infinity, and so the final potential energy, if I put infinity into this denominator, I'm going to get 0. And the final kinetic energy is also 0. So we end up with this expression for V1. And this turns out to be about 25,000 miles per hour. So if I look at the solutions, I note that there's really not a lot of difference in the speed between completely escaping the Earth and going up a distance RE above the Earth's surface. And the reason is, of course, is that the gravitational force of the Earth is strongest close to the Earth. And once I get pretty far away from the Earth, it doesn't take that much more energy to finally escape. And this ends example 13.5.